Hi everyone, in this lecture we are going to talk about how do you compute prime numbers efficiently using prime sieve. And the reason why you should definitely watch this lecture is because it's very important topic when it comes to competitive programming, and this concept can be used in a lot of problems that are directly related with finding prime numbers or a range of prime numbers. Okay, so it's very important you learn about various optimizations that we are going to discuss in this video, so that you can also submit those questions without getting a TLE. Okay, so let us talk about prime numbers. So prime number is a number that has only two divisors, one and the number itself. Okay, and the brute way of checking if a number is prime or not, you try to divide it by all numbers in the range 2 to n minus 1. If a number has any one of the divisor in this range, then it is not prime. Okay, for example, if we talk about the number 6, it has a divisor 2, so 6 is not prime. And if I talk about the number 7, so number 7 has only two divisors, 1 and 7 itself, so this number is prime. And the complexity of this brute force way would be order of n for one number. Okay, and if you have n number of numbers to be checked, then this complexity would be order of n into n, that is O of n square. Let's talk about a slightly better way. Okay, so a slightly better way is to see if we can iterate from, let's in this case we are iterating from I equals to 2 to n minus 1. We can also start by iteration from 2 up to square root of n. Okay, so in order to check if a number is n is prime or not, we can say, okay, we will only iterate up to root n and see if that number has any one of the divisor in this range. Why? So let me give you one example. If you have a number, let's say 36, okay, you will have various divisors. So one of the divisor will be 1 and one divisor will be 36, and we are not worried about 1 and 36, so we are worried about divisors which are in the range 2 to 35. Okay, so we have 2, we have 3, we have 4, we have 6, we have 9, we have 12. Okay, so clearly you can see these are the divisors of 36. So if you have at least one divisor, then this number is not prime. And also these divisors occur in pairs. Okay, so there is one more divisor, 18. So these divisor occur in pairs. So if you have 2, then you also have 18. If you have 3, you also have 9 or 12. If you have 4, you also have 9, and you also have 6 in this case, and 6 can be paired with itself. So clearly you can see under root of n is 6, so this is root n. So there are some divisors which are greater than root n, and there are some divisors which are less than root n. So if you have going to have a divisor which is going to be greater than root n, you will also have a corresponding divisor which is less than root n. So it is sufficient to check if a number has a divisor in the range 2 to root n. Okay, so this is one optimization we can do, and this is going to do significant reduction in the complexity. But again, this is not enough. So if you want to check if you have let's say you want to find all prime numbers in the range 1 to n. Okay, and in that case, for each number you will be doing root n time, and for n numbers the complexity will be order of n into root of n. Okay, so this will be the complexity, and let's say if n is 10 raised to the power 6, then root of 10 raised to the power 6 will be 10 power 3, and this would amount to 10 raised to the power 9 computations. Again, you can get a TLE. Okay, so this may again lead to time limit exceeded in this case. So we definitely need a better method, and this is where prime sieve comes into picture. So this is where we will talk about prime sieve. So if you want to see the implementation of first two methods, so you need to actually make a function called is prime. For a given number, you will check from int I equals 2, I less than n, I plus plus, if n modulus I is 0, which means this is not a prime number because we found at least one divisor. So the complexity of this brute force approach is order of n. And we can also do some modification. We can say, okay, we will check I square should be less than n. Okay, in this case this would be square root of n for one number, and for n numbers you can just call this function inside a loop, and you can see if a given number is prime or not. Okay, so the more optimized approach is a sieve based approach, where we will directly generate a range. We will directly generate an array containing prime numbers. Okay, so let's see how we can create a prime sieve. So let me give you one example now. Okay, so let's say you have an array like this, and let's say we want to find all prime numbers up to n equals to, let's say, 20 or something like that. Okay, so 2 3 4 5 6 7 8 9 10 12 13. Okay, so let's say you have an array like this, and what we will do initially, you will say, okay, all the numbers are prime. Let us assume all numbers are prime, and let's ignore one is not prime. Okay, and what we will do, we will go to 2 and we will mark all the multiples of 2 as not prime. Okay, so we will mark multiples of 2 as not prime, and this we will do for all the numbers. So multiples of 2 are 4, so not prime, 6 8 10 12 14 16 18 20. So these numbers are gone. Next we will move to the next position, and we will see if the given number is marked or not. So if the given number is not marked, it means we could not find a number which was less than 3, and that could be a divisor of 3. Okay, so which means 3 is also a prime. So what we will do, we will mark the multiples of 3 as not prime. So multiples of 3 are 6, it's already marked. 9, so we will mark 9 in this case, and then we have 15, we will mark 15, and that's it. Okay, so if we had 21, we would also mark it. So next we will go to 4. So 4 is not a prime number, so we will just skip this. From 2 we go to 3, and from 3 we will go to 5. And what we will do now is, we will mark those numbers as not prime which are multiples of 5. Okay, so mark multiples of 5 in this case. Now one thing to see here is, we can mark these multiples from 5. The very first multiple is 10, next multiple is 15, next multiple is 20, next multiple is 25, next multiple is 30, and so on. Okay, so we are going to go to these positions, and we are going to mark them as not prime. Okay, so 10 is already marked, 15 is already marked, 20 is already marked. So the very first multiple that is not marked is actually 25. Okay, so the very first multiple that is not marked is actually 25. So now there is a chance for another optimization. So let's discuss a chance for another kind of an optimization. Okay, so one way is, suppose you are at a number 5, okay, and you want to mark all the multiples of 5 as not prime. So you can say, okay, for let's say j equals to 2 into, let's say this number is number 2 into number, j less than equals to whatever is the max range, and I can say, okay, j plus equals to whatever is my number. Okay, so this loop, if you carefully see, okay, suppose we are currently at this particular number. So what I'm saying, okay, 2 into number, that means I'm going to 10, and whatever is my max range, let's say max range is 100 or 10 per 6, something like that. J plus equals to number. So every time I'm adding number to my j, so j will start from 10, it will go to 15, it will go to 20, it will go to 25, it will go to 30, and I can say, okay, primes of j is equal to false. So the jth number is not prime. This is one thing I can do. Okay, but we can further optimize this loop. Okay, so instead of starting from 2 into number, we can start from number into number. So that means we are starting from number square. Okay, so that means when I come to 5 or when I come to 7, I will directly start from 5 square. Okay, I will directly start from 25. So I will just skip this much part, and this will help me to reduce the number of iteration. And why this is true? Because if you talk about some number, let's say, which is just 1 less than 25. Okay, let's talk about a number 24. Let's talk about a number 25. And let's say you have a number 5. And just we saw that if you talk about divisors of 25, so you will have divisors which are, let's say, less than equal to 5, and there will be divisors which will be greater than equal to 5. Okay, and for 24 also, if this number is n, you will have at least some divisors which are less than equal to root n. Okay, and for 24 also, if you see, okay, you will have some divisors which are at least less than equal to 4. Okay, because we have already traversed this array, we have already traversed this part, so it means all the numbers in this range will have at least one divisor which is less than equal to 4. This is because of this property. Okay, let's say this number is n and this is root n. So for any given number n, there is at least one divisor possible which is less than equal to root n, if that number is not prime. So similarly for 24, okay, or all numbers which are less than 24, for example, number 10, number 15, number 20. So these numbers will have at least one divisor which is less than 5. This is what I'm trying to say here. So you do not need to mark these numbers as not prime, because they are also multiples of some other number which is less than 5. So we can just avoid this computation. Okay, so when we come to a prime number p, we will directly start by marking numbers from p square. Okay, and so we will, the first number that we will mark is p square. Okay, let's say this number is p, then this is p square. Next will be p square plus p, then it will be p square plus 2p, then it will be p square plus 3p, and so on. Okay, so if we do this, it will actually help us to optimize the loop. So this is one change that we are going to make here. Okay, what other optimization we can do? So far we have seen this was the first way, this was the second way, this was prime sieve is the third way, and this is the fourth optimization. Okay, and another optimization, fifth optimization that we can add in this video is, you can say all even numbers are not prime. Okay, you just go and mark the odd numbers. So we can say all even numbers can be skipped. Okay, we are not going to count any even number as prime, so it's not needed to mark even numbers. So you go and check only odd numbers and you skip all the even numbers. Okay, this is another thing that you can do. So I hope if you keep on doing this, okay, so if you keep on doing this for the entire array, what you will do, what you will see is, once this loop is complete, okay, once you go to every number and mark the multiples of that number as not prime, you will be only left with the prime numbers in the array. So let me show you. You are left with 2, 3, 5, 7, and for 7 you will just directly go to 49 and mark that number as not prime. 11, 13, 17, 19. Okay, so I have done this part for this array and I'm only left with the prime numbers. So 2, 3, 5, 7, 11, 13, 17 and 19. Okay, let's talk little bit about complexity also. Okay, so effectively what we are doing is, we are marking all multiples of 2 as not prime, so that will going to take n by 2 time. All multiples of 3, so n by 3 multiples, and we are going to iterate over them, and we are marking them as non-prime. Similarly, n by 5, n by 7, n by 11, and so on. Okay, and this is n followed by 1 by 2 plus 1 by 3 and so on. So you can see these are prime numbers. Okay, so I'm not going to prove this, but the summation of this series is log of n. So this comes out to be order of log of n. Okay, so this is the complexity of prime sieve, and you can see if n is a large number, let's say 10 raised to the power 18, then log of 10 raised to the power 18 is 60, and log of 60 is somewhere around 7. So it's just like order of n into 7. Okay, so this is approximately linear. Okay, so this is approximately linear. So you can see we have reduced our complexity from n square to order of n, roughly. Okay, and to be more precise, this is order of log of n. So this is the concept of prime sieve, and now we will implement this prime sieve and the optimized version. Okay, so let's see how we can implement the prime sieve. All right, so let me go here. Okay, so we will generate an array which contains prime numbers. So in the main I have created an array. So initially all the numbers are 0. Then I call this function prime sieve. The goal of this function is to fill this array with zeros and ones, and we will have 1 at those positions where the number is prime. So let's see how we can write the code for the prime sieve. Okay, so what I'm going to do, I'm going to first, so as I said, I will just skip all even numbers. So I will first mark all odd numbers as prime because they can be the potential prime numbers. Okay, so possibly some of the odd numbers can be prime numbers. So I less than 10 per 6. So this is my maximum value of n. Okay, I can say, okay, let's assume all odd numbers are primes. So I mark them as 1. So this is kind of an initialization. And this is where the sieve code is going to be. Okay, so for LL I equals to 3, I less than equals to 10 per 6. Okay, and I plus equals to 2. So clearly I'm just jumping over all odd numbers. Okay, and if I see if the current number is not marked, okay, is not marked, which means it is prime. So if the current number is prime, what we will do, we will mark all the multiples of this number as not prime. So if p of I is 1, which means the current number is prime, mark all the multiples of I as not prime. Okay, so you can say, okay, for LLJ equals to, now this is the loop I was talking about. So you can start from 2i. Okay, you can start from 2i, and then you can say, okay, j is less than equal to whatever is the maximum limit, and you can say j equals to j plus I, or j plus equals to I, and you can say, okay, p of j equals to 0. So here instead of doing 2i, you can also do I into I, because that is going to save more number of iterations for you without actually changing the answer. And that's it. Okay, so finally when you return this array, you will have only the prime numbers which are left in this array. And there are some special cases that we need to handle. So all even numbers are not prime except 2. So we have to say, okay, 2 is always prime, and we have to also say p of 1 is equal to p of 0, and this is equal to 0 because these numbers are not prime. Okay, so 1 and 0 will be 0. So that's it. And what I'm going to do is, now let's print primes up to, let's say, some range n. Okay, so what one thing you can do is you can make this constant as n, and for this can be defined in the question. So I've just hard coded for 10 per 6, and what I'm going to do is I'm taking input n and I'm just printing primes up to n, although we have computed all the primes up to 10 raised to the power 6. So let me just show you. So if the ith number is prime, we will print it. Let me run the code. So okay, so p of I, oh, this should be I equals to 3. Okay, that's it. So let me, okay, So if I print all the primes up to the range 100, I actually get this. Okay, and you can see, okay, we are not getting, oh okay, so one mistake is there. We have to skip for the, okay, we skip for the multiples of 2. Sorry, this should be here. Okay, this is one mistake here. So from 3 we just go to all the odd places. Okay, let me clear this and show you. Okay, so if I want all the prime numbers in the range up to 100, I'm getting all the prime numbers. Okay, although we are computing up to 10 raised to the power 6, so accordingly you can change this value, and this is how prime sieve works. Okay, so I hope this idea of prime sieve is clear, and you will definitely find it useful in many of the problems in competitive coding, and we will also make use of it to solve some hacker blocks problems. Thanks a lot. See you guys in the next video.